All right, let's walk through an item analysis together. So I have on Canvas some just some example test data. We basically gave a stat quiz to our class, and we want to analyze how well each item performs on the quiz. So here's our example quiz. And for each question, you're supposed to circle the correct response. So, for the first question, the probability of rejecting a false null hypothesis is known as what? So that'd be known as, 1 minus beta, or the power of the test, right? Question 2, for this type of correlation, the variable changes in the same direction. That'd be a positive correlation, right? So in the Excel file here, list, the question number and then each student's response to the question. So the first student said C. The correct answer, I believe, was D, wasn't it? Yeah, correct answer was D. Number 2, the correct answer was A. So you can see person 5 here on line 5 at least got the answer for number 1 right. Looks like everybody got the answer for number 2 correctly. So these data, there were 20 questions. I also have some information about whether they were male or female, and whether they were a psych major or not. And then on down, and at the end of the data set is basically their is the item dichotomously scored, whether or not they got the question correctly or not. So you can see person 5, remember, got item 1 right, and item 2, everybody got correct. See, so they all have a 1. Also calculated a total score. So out of a total of 20 possible points, person number 1 got 8. Person on row 11 here got 16 out of 20 correct, or about 80%. Also created some percentiles. So the top 2 scores would be the top 25%. Since we had a tie down here, put all 3 in the bottom quartile. So basically computing some of these item analysis statistics is actually pretty easy, right? The item difficulty is just the average score for that item, so just a proportion of people who got the item correct. So for the first one, 10% of people got it correct, so the item was actually quite difficult. For the second item, the difficulty is 1, saying everybody got that item correct. Let's just drag it on out to all the scores so we can see. Looks like number 6 was fairly challenging. About 60% of people got it correct. Number 3, only 30% of people got it correct. We also want to know how our items discriminate against each other, discriminate between high and low performers. So we could calculate like the discrimination index. Let's calculate, so for get the sum of the scores in the high group, the average of their scores, minus the average score for those in the bottom group. So it's 3 of them. So it has no discrimination, right? It just drug out the formula for the rest of the items out there, right? It doesn't do a good job of discriminating between high and low ability students, basically because none of the high and none of the low ability students got it right. Same thing with question 2. It doesn't do a good job discriminating because everybody got it right. Number 3 has a negative discrimination. So this is basically saying that lower ability students are more likely to get this question right. So that means, or I guess lower performing students are more likely to get this question correctly. So that's saying, hey, something might actually be going on with this item. A good performing item should be one that that can differentiate between those who score well on the test and those who score poorly on the test. This is indicating that those who score lower on the test tend to get this question right. So something's going on with this item. We can look, questions 6 and 7 seem to have a decent difficulty and decent item discrimination parameters. Those who perform well on the test tend to get these items correct. Thinking about the discrimination index is we're ignoring more than half of our data, right? There's only 5 people we've been using to calculate the discrimination index. There's another 5 that we're ignoring in this data set. So that's why sometimes we do like the point biserial correlation, which is just the correlation between whether you got the score right on the test or not and the total score. So we can see here we have a negative discrimination. This is kind of weird because only one person got the answer right here. Whoops, I know what I did. We need to tell Excel, don't move. We want to keep that the same. There we go. Now we have our point biserial correlation. We don't get a discrimination here because everybody got the question right. So we can see here we still have negative discrimination on question 3. Right, the lower ability students tended to get this question correct more than the high ability students. And if you notice here, if you notice the test scores here, they're sort of sorted in descending order here from lowest ability to high ability. So you can kind of look through here and check too. It looks like question 6 here does a pretty good job of discriminating between high and low ability students. So does question 7. Question 5, only the one who scored the highest on the quiz got question 5 correctly. Question 8 does a good job discriminating between low and high ability students, and you can really see that in the pattern here. We usually report a correction to the point biserial correlation, and that is the correlation between the data set. Between whether you got the question right or wrong or not, and the total score minus that particular item. And I want to make sure when I drag it that this column doesn't move, because we would expect an item says, this is basically the item test correlation, and so you'd expect the correlation between an item and the total that includes that item to be highly correlated. And so you can see for questions that function properly, like 5, 6, and 7, the corrected correlation's a lot lower than just the regular point biserial correlation. And you can see it's even worse for items that don't behave well. It's saying that, hey, something's really going on with questions 1 and 3. We want to take a look at and see what's going on there. So, in all, a lot of these item statistics are not very difficult to compute by hand. I just showed you how to do them really quick in Excel. I'm also going to show you how to do these in Stata as well. The same concepts that I talked about here apply to do a distractor analysis. Basically, we do a distractor analysis. We're going to take our item set. So let's just copy this. Let's do it. And we'll just compute the point biserial correlation between this item set and the total. It's not going to like this because these aren't numbers. So we're going to say, so in this time we're going to dichotomize it so let's say for those who selected A. So we'll give a 0 if you didn't, a 1 if you gave A, 0, a 0, a 0, a 1, a 1, a 0, a 0. So here's our discrimination index for the distractor A, for those who chose A for question 1, actually has. So for distractor items, we want them to have negative discrimination. All right, we want those who perform high on the test to not choose those as often. And it looks like those who are performing higher on the test tended to choose A more often than they should. That's the basic idea of a distractor analysis. We could do the same thing that was with A. We're going to do the same thing, but with anybody who has a B. So that's still 0, 0, 0, 0, 1. And then we get our discrimination in parameter here. So, yeah, higher ability students were, again, more likely to choose B as well. Remember, question 1 wasn't a good performer anyways. Plus, only one person got the question right. We could let's look at question, let's do the distractor analysis for item 5. What was the answer on 5? Supposed to be B. Now, this is one where only one person got it right. So if we did D, you can see D was it's probably a pretty good distractor item. So typically for the wrong answers, we want to see lower discrimination values or even negative values is a good thing for those. I found there's a really cool program in Stata